Hi, this is Jeff Heaton. In this video, I'm going to show you how machines learn. We're going to look at what is really happening underneath the hood of models like neural networks and how they actually learn from data. We're focusing specifically on supervised learning. Okay, just to level set, we are dealing with supervised learning. So in this case, we are looking at how would we predict that health score given age, gender, height, weight. We know the value for 3 of them. How would we predict the 2 that we do not? We're using past data to predict future data. Supervised learning. Well, what can go wrong with this? There's bias. That's where the model that you're using, such as a neural network or GLM, just the shape of data that model is able to learn, your data just do not fit into that. So that is something that you can overcome by using multiple models or just using a different model. Maybe the data just don't fit the model that you're using. Then there's variance. This is error in your data that is caused from your data because you just don't have values that will let you predict certain things, or noise in your data, or other cleanup that maybe should have been done with your data. So let's look at how you would learn something like this. Let's look at a really simple example, converting Celsius to Fahrenheit. There's formulas to do this, but that formula is actually a model. So let's see here, we have certain Fahrenheit values that we know and others that we do not know. And how would we convert from Celsius to that? Here's the formula that everybody learns to convert the data. This is a simple linear equation. You have a slope and you have an intercept. The slope is m, the intercept is b. This is fairly basic algebra. But we can think of this as a machine learning problem. Think of that linear equation as a general model. This is a GLM, one type of GLM anyway, for learning purely linear data. How would you figure out what those two b's are, beta 1 and beta 2, to fit the equation to the temperature data? One of the b's is going to be 9/5, the other is 32. You know this because you saw the formula, but you could use this linear formula as a model and predict those two values some way. And you would come up with those two values. You could just try random values until you get something that closely matches the data, or you could use gradient descent or other approaches. But that is learning. Those are like the weights of a neural network. That is what you are learning to fit the data more accurately. It's a simple linear model. So if the temperatures had a curve in them, that would be bias error because you just would not be able to get that line to fit perfectly to the data. So that is bias. Variance would be if those temperatures that you had, if some of them you just didn't get very accurate, or if there's just noise in the data. Let's look at wind chill though. Wind chill, now you have more than one input variable. You have the wind velocity and the air temperature. So for this, we have several exponents that are introduced for the velocities, and this equation will essentially give you the wind chill. This is a lot like a model. You could basically have figured out what the wind chill is just by how it actually feels to you, and then try to fit the velocity and air temperature so that you can calculate this. So this is the formula for wind chill. There's 2 variables, so now you can't just plot it on a simple line chart. You need a heat map. And the heat here does not refer to the temperature necessarily. Any 2 variables can be represented in a heat map. A heat map shows you the interaction of 3 variables where 2 are being used to predict. So temperature and wind are being used to predict the third one, which is the color, the heat, which is the wind chill. The heat index. So here we are using we're calculating the heat index. We're using the temperature and the relative humidity. So when it's cold, how cold it feels has more to do with the wind speed. When it's hot, the relative humidity plays along with the temperature. Look at all those constants in this polynomial. It's a polynomial because all the powers are even, r squared, and it is a 2 variable input. those C's, the constants, this was probably determined with polynomial regression, which is a way that you can fit the data to that polynomial. Now, polynomial, at least this degree of 1, looks very much like a parabola. So if the data don't fit into a parabola, you're going to have bias error. But here is the heat map showing you the interaction between temperature and relative humidity. Now, if you have a very complex relationship like this heat map, it's very, very difficult to fit a model to it, because most of the models, they want very convex search space like this, so that you can almost think of it like a marble rolling down a hill. If you've got this going on, it's a lot more difficult to predict. So now let's try something that doesn't fit into one of those simple linear models like we've seen so far, or to the polynomial. We're going to write something that tries to calculate the real feel. You only use heat index when it's warm, you only use wind chill when it's cold. So let's create a data set that has the real feel temperatures calculated. It'll use heat index when it's warm, it'll use nothing in the middle, and it'll use wind chill at the bottom when it's cold. So here in Python, I've created a couple of functions. I've created a heat index. This is basically just what we had before. Calculate wind chill, same equation as what I showed you in the slides. And then real feel, if it's greater than or equal to 79, I'm going to use heat index. If it's less than or equal to 40, I'm going to do wind chill. So these are Fahrenheit temperatures, which is what these work. Here, we'll go ahead and run it. We'll run it with my 2 test cases, and you can see it is calculating that. Now I'm going to generate a CSV file, and I'm essentially going to do a cube. So I'm going to loop across a bunch of temperatures, a bunch of relative humidities, and a bunch of velocities, and I'm going to go from -2 to 90 in the temperature range. I'm choosing 90 because I want to test extrapolation. So we can throw in a 95 and see how well the models extrapolate outside of the range that they were trained with. And here's a hint, they don't do this real well. And then we're going to do relative humidity from 1 to 100, velocity from 0 to 100 miles an hour. So the 5s here, this just shows how far you go. So it's going to start at -20, then go to -15, then -10. So it's going to count up by 5s. This does 2 things. First, it keeps the data set reasonably small, and secondly, it lets me test interpolation if I want to. Interpolation is how well does the model generalize on values that are in between training set elements. Extrapolation is outside the range, interpolation is within. Let's go ahead and run this. Generates the file. We're going to use RapidMiner to look at this. RapidMiner can very quickly automatically generate a model. It doesn't generate a great model, but it gives you a starting point. So this gives me a nice language and model agnostic way to look at how we would do this. So I'm going to do AutoModel, and I am going to use the local repository, and here is my real feel data set that I generated. Next. This shows you what it looks like. You can see I just looped through these 3 values and generated the actual real feel temperature. We're going to predict, and we're going to predict real feel. Next. It shows me some distribution sort of information. That's not important really for what I'm doing here. Next, and run. So now it is automatically creating a GLM model. You can see the GLM didn't do too well. It's ±9 degrees. Decision tree did excellent, or at least it appears to have. Really hasn't, but it gets a perfect, highly overfit root mean square of 0. And the random forest and gradient trees are still running. I can go to the deep learning model. And here I can enter these values for anything that I want to, and it is going to give me a prediction of what it thinks the real feel would be. So I'll do a relative humidity of 30, temperature of, let's do 80. Wind velocity doesn't really matter because we're in heat index range. But there I said it's 80 degrees, 30 degrees relative humidity. What does that feel like? It says it's going to feel like about 78 degrees. All right, if we calculate this using the National Weather Service's calculator, we'll see that it is 79 degrees. So it was pretty close. This is interpolation, especially if we move it to an uneven number like 83. If we move it to 83, it now says it's 80. If we move the temperature here to 83 and calculate, 81, so it's still pretty close. Let's make it now extrapolate. Doesn't typically do as well on that, so we'll do, I don't know, we'll do 105. Now see that red? That's RapidMiner saying, hey, you're cheating. You're giving me a value outside of my range. I know I'm not very good at that. Most models are not. So if we do 105 over here and calculate, it should be 112. However, this is saying 96. So extrapolation is not real powerful for these types of models without you doing some feature engineering or something. Extrapolation is always hard because you're outside of your range. If we do a decision tree that got that perfect score, it would not do particularly well either. If you look at this complex tree that it's built, it is basically overfitting. It is essentially memorizing the data. We did not have a large amount of data, so it just memorized it. So it would not extrapolate particularly well. If you try to interpolate even and go between the values that you trained it on, pretty much everything in between those fives that we counted up by will be the same value because it's simply memorized. In this video, you saw how machines learn. Basically, what they're doing is creating very complicated equations. For some models, they create fairly simple equations like polynomials or linear models that you can take a look at. However, if you're using something like a neural network, fundamentally it's doing the same thing. It's just doing a very complex equation and adjusting coefficients, which are the weights, so that the data fit the expected value close to what you're saying it should for supervised learning. Thank you for watching this video, and if you found this interesting, please post any questions you have in the comments or give me a like. If you'd like to see more like this, subscribe to my channel. Thank you very much.